Hello, everybody. Today we're going to be talking about Chapter 7, Lesson 6, something known as exponential growth and decay. Now, we should have already talked about exponential functions. This is a specific type of exponential function that's generally used to describe things that grow or things that get smaller. A lot of times you see this used, especially in money and things with interest, and we'll see that today. You also see it with population, either growth or decline. So today the two objectives are going to be solve problems involving exponential growth and solve problems involving exponential decay. So we'll start with growth. So obviously if something's growing, it is getting bigger. So here's our general equation for exponential growth. We have y is equal to a times the quantity of 1 plus r, all raised to the t. Okay? In this case, a is our initial amount, 1 is a constant, r is our rate expressed as a decimal, okay, and t would be time. And also y represents our final amount, okay, or where we end up. So if we take a look at an example here, example number 1, it says the prize for a radio station contest begins with a $100 gift card. Once a day, a name is announced. The person has 15 minutes to call, or the prize increases by 2.5% for the next day. So we want to write an equation to represent the amount of the gift card in dollars after T days with no winners. So what we can do is we start with our general form. Y equals A times the quantity of 1 plus R, all raised to the T. And what we plug in is what we know. Okay, so we don't know the final amount, so that stays as y. Our original amount is going to be the $100 gift card. 1 is always 1, and our rate is 2.5%. Now, 2.5% as a decimal would be 0.025, so that's what I put in there. All raised to the t. Okay, you may leave it this way. I prefer it this way. It's very easy to see now what the rate is. Some people may simplify it down to this, 1.025 raised to the t, because all you do is take 1 and add it to 0.025, but I would really prefer this one. Okay, so that would be our equation. Now, how much will the gift card be worth if no one wins after 10 days? Well, now 10 days represents t for time, so we plug that in for t into our original equation. To the 10th power. Now you may see why some people want to simplify it like this, because when you start to plug in, your first step is going to be to add these two together anyway. Okay, so y equals 100 times 1.025 raised to the 10th. Now here, all I need to do is simplify my equation. So using my order of operations, I know I'm going to have to use that exponent first. Okay. So I take 1.025 raised to the 10th power. And I get a very long decimal. Y equals 100 times, ready? 1.280084544. Okay, now when you multiply by 100, all you need to do is move the decimal places 2 places to the right, so y would equal 128.01. Okay, if we round to 2 decimal places, why would I round to 2 decimal places? Because I'm dealing with money. Now, if you are good with your calculator, you can plug this whole thing in, but make sure you put parentheses around the 1.025. That way you're not raising the 100 to the 10th power. That would result in an incorrect answer. So, go ahead, try this one on your own. Try number 1 on your own under the guided practice. I'll be back in a minute to go through that one. All right, we should be back from trying number one. Let's go through it. A college tuition has risen 5% each year since 2000. If the tuition in 2000 was $10,850, write an equation for the amount of tuition T years after 2000 and then predict the cost for 2015. Okay, so y equals A times 1 plus R to the T. A is the original amount. Y equals $10,850. 1 plus, what's the rate? 5%. As a decimal, 0.05 to the T. That would be our general equation. Now we can figure out the price of tuition based on this increase each year for any of the years. So this is how we can predict the cost of going to college, say in 2020 or whenever you guys will head. Okay, so now we plug it in. Y equals 10,850 times 1 plus 0.05, all raised to the, okay, so how many years from 2000 to 2015? 15 years. Okay, so y equals 10,850 times 1.05 raised to the 15th power. This time I'm going to plug it all into my calculator, and I know my calculator is a little bit different than yours, but just to show you, 10,850 parentheses 1.05 all raised to the 15th power. That should be our answer. So y equals $22,556.37. So you see how quickly the cost of college can rise, even with just a 5% increase each year. Okay, it gets out of control. All right, moving on. The next thing we want to take a look at is something called compound interest. So this is a different type of exponential growth. It's specifically used in financial settings. We talk about different ways interest is compounded. You may have heard that savings accounts have usually a 1 to 3% interest rate, but how often is it compounded is really the key on how much money you're going to make on them. If they're compounded yearly, you're not making very much money on them. Compounded monthly or weekly, now you are. So compound interest is interest earned or paid on both the initial investment and previously earned interest. It is an application of exponential growth. So our equation is a little bit different. A equals P times the quantity 1 plus R over N, all raised to the NT. So A is the current amount, okay, or your final amount. P is the principal, or your initial amount. R, as always, is the rate expressed as a decimal. N is going to be the number of times the interest is compounded each year. Okay, so if it's compounded yearly, that would be 1. If it's compounded monthly, that would be 12. And T is your time in years. Okay, time in years. So let's see how this works. Maria's parents invested $14,000 at 6% per year, compounded monthly. How much money will there be in the account after 10 years? Okay, so we start with A equals P times quantity 1 plus R over N to the NT. Okay, now we plug in the information that we know. Okay, I don't know how much it's currently worth. I know how much we started with though, $14,000. 1 plus. Now my rate was 6%, 0.06. N is how many times it's compounded per year. So monthly would be 12 times per year. So 12 goes on the bottom. And again, N, that's the same thing. So 12 times, and my time would be 10 years. So now, really, to find my answer, all I need to do is simplify a lot of this equation. Okay, so 14,000 times 1 plus, what's 0.06 divided by 12? 0.06 divided by 12 is 0.005. 5. And 12 times 10 is 120. So again, I'll simplify a little bit further here just to make it easier to put into my calculator. 1.005 to the 1/20th. Again, I'm going to put that whole thing right in my calculator. It's just easier. Let's see if I can get to a point where you can see. 14,000 times 1.005 raised to the 120th power. So the value of this account after 10 years will be $25,471.55. So that's a pretty good investment after 10 years. All right, go ahead and try the guided practice number 2 on your own. I'll be back in a minute to go through it with you. Okay, we should be back from trying number 2. Let's talk about it. Determine the amount of an investment if $300 is invested at a rate of 3.5% compounded monthly for 22 years. Okay, that's a long investment. Start with your equation. A equals P times 1 plus R over N raised to the NT. Plug in the information that you know. I don't know what it's currently worth, but I know we started with $300. 1 plus, what's the rate? 3.5%. Do not forget to write that as a decimal. It must be written as a decimal. 0.035. How many times is it compounded per year? Monthly? Well, that would be 12 times. So 12 times, and how many years? 22. Simplify. A equals 300, 1 plus 0.035 divided by 12 is 0.00291, and we'll round it to 67. 12 times 22 is 264. One more simplification here. I screwed it up. Here we go. One more simplification. 300 times 1.002967 to the 264th power. And we'll plug it into the calculator. 300, you can put it in just exactly how it's written. 0.0029167 raised to the 264th power. And after 22 years, we managed to almost over double our money. $647.21. Now, one thing I want to talk about here is notice when I simplified here, I rounded this decimal. This decimal went on further for about 5 more digits or so. If you are really good with your calculator, you can type this entire equation into it, but you need to be very careful. Okay, let's see if I can get it done correctly here on the first try. So 300 times 1 plus, now I need another set of parentheses for this fraction. 0.035 divided by 12. Close those parentheses, the ones for the fraction. Close the ones with the 1, okay, and then raise it to, and now since I'm multiplying these two together, I want to put another set of parentheses by the 12 and the 22 just to make sure that those are multiplied before we raise it to that power, okay, and if we hit enter, notice we get 647.204. So if we're rounding to 2 decimal places, now we're 1 cent off. Okay. Now, for us in 8th grade math with our account, 1 cent difference, not a very big deal. But if you're Wells Fargo, U.S. Bank, one of those giant corporations that do thousands and thousands and thousands of transactions like this every day, if you're 1 cent off on all of them, okay, that can amount to a very, very serious amount of money. Okay, So it's important that we can be as accurate as possible. And in order to do that, we need to take full advantage of our calculator and use it correctly. All right, and I can help you with that later if you struggle. All right, the next thing, the last thing we have to talk about here is exponential decay. So exponential growth has to deal with things getting bigger or larger. Exponential decay has to do with them getting smaller. So the equation for exponential decay is essentially the exact same as exponential growth, except now instead of adding in the middle, we are subtracting. So y is still your final amount, a is the initial amount, 1 is a constant, r is your rate expressed as a decimal, and t is time. So take a look at example number 3. A fully inflated child's raft for a pool is losing 6.6% of its air every day. The raft originally contained 4,500 cubic inches of air. Write an equation to represent the loss of air. So we'll start with our original, y equals a 1 minus r to the t. Okay, so y would equal our original amount is 4,500 times 1 minus our rate, 0.066, all raised to the t because we weren't given a time length. Okay, so that would be our equation. Okay, now it says estimate the amount of air there in the raft after 7 days. Okay, so y equals 4,500, 1 minus 0.066, all raised to the 7th power. Now again, after the compound interest, the same thing is true for growth and decay. If we want our most accurate answer, we can put the whole thing into our calculator. 4,500 times 1 minus 0.066, all raised to the 7th power. So y equals 2790.23, and remember our label, cubic inches of air. So that would be our estimate for how much is left. All right, exponential decay is very, very, very similar to exponential growth. Like I said, the only difference is things are going down instead of up. Okay, go ahead and pause the video. Try guided practice number 3. I'll be back in a minute to go through it with you. Okay, you should be back from trying number 3. The population of Campbell County, Kentucky has been decreasing at an average rate of about 0.3% per year. In 2000, its population was 88,647. Write an equation to represent the population since 2000. If the trend continues, predict the population in 2010. Okay, so y equals a times 1 minus r to the t. Plug in what we know. Our original amount, 88,647. 1 minus our rate. Now, 0.3% as a decimal, 0.003. 2 places to the right. And raised to the t. So first it says write an equation to represent the population since 2000. That would be to the t. Now if we want to figure out or predict the population in 2010, we plug in 10 for the years. So again, I'm going to plug the whole thing into my calculator. All raised to the 10th power. And we get our answer of 86,023. Yes, 23 people. Now, why would I round to the nearest whole number? Well, because I'm dealing with people. Okay. People are whole. Okay, so that is exponential growth and decay. One thing that is really cool and neat about exponential growth and decay is we can take a lot of data from the history and use it to predict the future. It's a mathematical prediction. It's an educated guess, and it's essentially saying if this trend continues the way it has, this is going to be the result. So a lot of the scientific stuff, a lot of any predictions about the future that you see, any valid ones are going to be based on some sort of mathematical reasoning, such as exponential growth and decay. If you want to know why you can't get a deer hunting license in North Dakota, it is because of exponential growth and decay. They take a look at the population, they take a look at the rates that they've been going at, and they make an estimation. Now, with populations, especially in animals, there's a whole lot more that goes into it than just a simple math equation, but the concept is the same. Okay, and this does play a role into it. Okay, but they have a whole host of other factors, available food sources, available habitat, predators, and things like that go into setting it. But the population growth and decline is based off exponential growth and decay. So here is the assignment. Go ahead and get started, and have a great day.